Good morning, everyone. Just to start today off, so it's a pleasure to have Jordan Cotler telling us about quantum mechanics of the Hartle-Hawking state.
Well, thank you so much for giving me the opportunity to speak. So I'm going to tell you about some work on de Sitter quantum gravity, specifically about the Hartle-Hawking state. So this is a combination of work that was done in collaboration with Christian Jensen, that came out last year, and some more recent work that came out in January. So I'll speak a bit about both. So let's begin. So in this talk, we're going to be concerned with the wave function of the universe, or at least a wave function of the universe, whether or not it is the wave function. And this is a particularly famous wave function of the universe due to Hartle and Hawking in the early 80s, and I'll tell you quite a bit about it. And the basic picture is that we want to imagine that we're considering Einstein gravity coupled to matter with a positive cosmological constant as salient for instance computing, doing cosmological perturbation theory. That the universe starts off in some no boundary state and terminates in some asymptotically de Sitter region. Now in the no boundary state, we usually consider a sum over topologies. So this is the leading contribution in which the spatial cross sections are spheres, or d-1 spheres, and then you can also have other cross sections as well that correspond to more interesting manifolds. In this talk, we're going to be concerned with the leading contribution, the so-called largest contribution to the no boundary state, which is takes the form of the Hartle-Hawking geometry, which I'll write down a little bit. So this is really the canonical Hartle-Hawking state, which you can view as part of an expansion of the no boundary state, which also contains the higher topologies. There's a lot of, so the basic architecture of this state is that you imagine that the state terminates in some asymptotic metric, some metric at asymptotia that I'll call gamma. So this is a metric on the d-1 sphere at conformal infinity. And this is the form of an asymptotically de Sitter geometry in Pfefferman-Graham gauge, or Pfefferman-Graham coordinates. So at large positive t, we have this exponential factor up here, and then we have the leading spatial metric gamma ij. And the way that we're to think about this is we can take the Hartle-Hawking state, I'll put this in double brackets to remind us, or double caps to remind us that this is a gravitational state, that we are expressing the Hartle-Hawking state in the gamma basis, in the basis of these metrics at asymptotia. And I'll write this as the Hartle-Hawking wave functional as a functional of gamma. So here's how you should think about this. You should think about this in ordinary quantum mechanics. Maybe I'll write something over here. If I just have single particle quantum mechanics and I have a state psi, I can expand it in the x basis, and that gives me some psi of x. So I have this state, and the x is tantamount to a choice of basis. Here, the fact that the metric at asymptotia is gamma is tantamount to a choice of basis in which to expand the Hartle-Hawking state, which then gives us the Hartle-Hawking wave functional. So it's exactly analogous. There's many basic questions that one can ask about this state. And some of them, for example, are what are its correlation functions if we want to compute, in the context of an inflaton, we want to look at, for example, Gaussian and non-Gaussian fluctuations of the gravitational field. But one of the more basic questions is just to ask, what is the norm of the Hartle-Hawking state at loop level? And I'll tell you why this is an interesting question, even though it might seem mundane to compute the norm of a wave function.
So can I ask a basic question?
Of course.
Is it obvious that this gamma is a basis? It's complete, it's orthogonal, spans the whole inverse space.
Yeah, so I'll tell you what I mean by it, and then we can talk about whether in fact it's a basis. But what we really want is that, when we say that x is a basis, okay, of course, x is not an L2 basis, famously, in quantum mechanics. It's delta function normalizable as opposed to an L2. But what we really want is that in quantum mechanics is that when we integrate over x's, they form a resolution of the identity. And what we really want here is that these gammas form a resolution of the identity. Namely that there's a way of cutting and gluing these spacetimes together at this surface. That if we integrate over all of these gammas, if we glue, for example, ket to the bra, that it sews them together in a way which is consistent with a certain set of cutting and gluing rules. And that we'll take as being tantamount to whether it furnishes a resolution of the identity. But let's hold that question for a moment. It's a good question. So relatedly, what does it mean then to do this gluing of the Hartle-Hawking state in this gamma basis? Well, what it means is that you want to take the norm squared of the Hartle-Hawking wave functional, and you want to integrate it over all gamma. But there's a gauge redundancy in how you define gamma, which is that gamma, since it's a metric at asymptotia in the spectrum and grand expansion, is only defined modulo diff times vial. So therefore, the natural proposal that people have mentioned before is to integrate over all gamma modulo diff times vial and to take this as the inner product. And we'll see what the consequences are of this shortly. But this is tantamount to an insertion of a resolution of the identity in the gamma basis, accounting for the gauge redundancy in the definition of what gamma is. And the question is, what does this equal? So why is this an interesting question? Well, what would you guess the answer to be? So if you took, again, the ket and you root it to the bra, well, again, the Hartle-Hawking state has this Euclidean cap. It has this Lorentzian de Sitter expanding throat. If you were to glue it to here, the natural guess is that maybe it should be the sphere partition function. And indeed, this is true at tree level. However, if you were to venture this guess, then you would run into a problem. So, due to work of Polchinski in '89, and maybe recently elucidated the very beautiful paper by Hurston, Eflat, and Son, you can compute the sphere partition function to one loop. And what you find is that, so it has this term which is exponential in the entropy, but you have a term which goes like I to the d plus 2 if you're in d total space-time dimensions. So this factor of I to the d plus 2, again, this is just the sphere partition function. I'm not saying that it equals this. I'm saying, suppose they're equal, what would be the consequence? The sphere partition function has this pesky factor of I, and it's related to the fact that in gravity there's a wrong sign conformal mode, in Euclidean gravity. This would be a bad answer to get for the norm of a state. This is not positive. It can be imaginary in different dimensions. This would be very, very weird indeed. So it's not, in fact, obvious what the answer should be, why these two should agree beyond tree level. The tree level contribution is basically just this term. But at loop level, you get these extra factors of I and extra one-loop determinant pieces. As an aside, as you may have heard, there's been a number of recent works which have been interested in this factor of I to the d plus 2. This is problematic for another reason, which is that famously, the sphere partition function is supposed to tell us about the de Sitter entropy of the static patch. So having these factors of I is not good for that either, because the static patch entropy should be a real number as opposed to imaginary or negative. Nonetheless, this is another, so I want to pose this as a question. So what is the norm of the Hartle-Hawking state? Is it the sphere and we're afflicted with these factors of I? Is it something else? Now this is consequential for the following reason, is that we would like to use the Hartle-Hawking wave function for cosmological perturbation theory to predict things about the CMB. So these basic considerations of if its norm doesn't make sense would be very strange indeed. So then what I'm going to show you is that the answer looks a little bit different. If you do a one-loop computation of the norm of the Hartle-Hawking state, which I'll say what it means to do it to one loop, what you find is not the sphere partition function, but morally speaking, you find the absolute value of the sphere partition function, and divided by the volume of the de Sitter isometry group in d dimensions, which is the volume of SOD1. Now the volume of SOD1 is a non-compact group, so this volume is infinite. If you take a finite number and divide by infinity, you get 0. So that would give you that the Hartle-Hawking wave functional is actually a null state at one loop. And in fact, this persists to all loops from perturbation theory for pure gravity or pure gravity coupled to Bunch-Davies matter. As a quick comment, maybe I'll write this on the board. In the sphere partition function answer, for the sphere partition function is basically a number times I to the d plus 2 divided by the volume of SOD plus 1. So this volume of SOD plus 1, or these volume factors of isometry groups in the denominator are happen in various places. But in the sphere calculation, it's the division of the volume of a compact Lie group. What's funny in this case, but very important ultimately to the physics, is that for the Hartle-Hawking calculation, the norm of the Hartle-Hawking, it's the division by the volume of a non-compact Lie group. And that's what leads to 0. So this is another sense in which the answers look similar but different from one another. So therefore, the Hartle-Hawking state is a null state at one loop. And as I said, also when you couple it to Bunch-Davies matter, when you couple it to matter fields that are jointly prepared in the no-boundary state. So the goal of this talk is to explain to you this calculation, and then to tell you why it's robust, what its physical interpretation is, and then maybe speculate on what it means for quantum cosmology. That last part is the most speculative part. I don't totally know what it means for quantum cosmology.
Can I ask?
Of course.
So would you be able to use your method to compute the norm at early times?
Excellent question. So in some follow-up work with Christian and Joaquin Toriachi and Xiaoyu Shi, his student, we have been doing this computation at finite time. And at finite time, you need a different gauge fixing because, in other words, there's a different gauge redundancy in finite time slices vis-a-vis infinite time slices. But one can take care of that in some appropriate way, and we find the same answer.
But should I expect that it continuously goes from this to that or not?
It doesn't. It stays this.
But if I go all the way to the neck of the seed, shouldn't it go back to the...
Yeah, that's a very good question. So the thing that, so this is the thing that we're still sorting out, so let me say it in a more tentative way. The thing that is important in this calculation is that there's a Lorentzian inner product. This is different from a Euclidean pairing, even though the pictures look very similar. So it seems that there are two different ways of doing the gluing. One of which is the natural thing of essentially quantum fields in Lorentzian signature that gives you this. But if you do a Euclidean gluing, then it seems that you can get the other answer, namely the sphere. Now, interestingly, there's two different ways of doing the Euclidean gluing, and depending on the way of doing them, you might get this or the complex conjugate. Something you might have wondered about the Polchinski answer is why it's I to the d plus 2 and not minus I to the d plus 2. So that there might be a way of understanding this, but that's still tentative at the moment. But that is all to emphasize that there really is a difference between Euclidean gluings and Lorentzian gluings. They're different ways of doing gluings. That's something that is illuminated by doing the finite time analysis. Let me first review what we mean by the inner product on asymptotic states, and then we'll elaborate on it in various details. So these authors here propose that this is the natural inner product on asymptotic states. As I mentioned before, if you have a metric gamma at conformal future infinity, it is defined modulo a diff times vial redundancy. So when you want to glue psi to itself, some wave functional of gamma, then you need to divide by this gauge redundancy so that you don't overcount. They did various calculations along these lines, and it's related to the story of group averaging, at least when you do this around a de Sitter, an ordinary de Sitter geometry. I can explain the connection to group averaging later on. So therefore, the resolution of the identity that one gets that corresponds to this is saying that if you have gamma, that if you integrate over gamma mod diff times vial, this is supposed to be a resolution of the identity. Now, this, if you like, is a kind of is a guess that one can make. It's related to your question. You know, is this actually a good inner product or really a resolution of the identity? And the answer is that one needs to check it by seeing that it satisfies. You know, for example, it should be the case that if you multiply this thing by itself, you should get back the identity. The identity times the identity should be the identity. You have to check various compositionality properties and gluing rules to check if this actually makes sense.
For instance, these metrics are on the sphere topology, or should some overall spatial topologies?
So we're working at fixed topology, which is the leading contribution to the no boundary state. So you can think about these gammas are metrics on the d-1 sphere. The d-1 sphere at future infinity. Yeah. You're integrating over these metrics on the sphere.
Where is the lie coming from?
It's related to, if you like, time reparameterization. It's your sort of choice of the cutoff slice.
Okay, so it's yeah, okay. I would call it diff. So it's not that there is any. So it's just because the theory is diffeomorphism.
Yeah, it's because the bulk theory is diffeomorphism.
Yeah,
And that's
yeah,
sort of
okay.
open boundary. Yeah, yeah. So let us proceed to compute the norm of Hartle-Hawking to one loop. We'll do this first in pure gravity, I mean Einstein gravity. And we can, I'll tell you later what happens when we couple to matter. It won't complicate things that much. And let's see what the steps are so we can inspect how we get to the final answer that I stated. So here is the same formula that I wrote down before, norm of Hartle-Hawking. But let's expand this out. So what do we mean by this wave functional of gamma? So what you mean by the wave functional of gamma, what you do in the path integral, schematically, is that you consider the bulk path integral, where you integrate over all smooth geometries that terminate in some boundary with metric, asymptotic metric gamma. And so this is the Einstein-Hilbert action with appropriate boundary terms. And this is how you prepare the wave functional. This is the usual procedure in the path integral to prepare wave functional on some slice. And what we're going to do then is to take this object and we're going to integrate this over gamma. Because this is the same thing as as psi, the Hartle-Hawking psi of gamma. Now, there is a nice simplification of this that will be useful for us, which is that when we integrate this over all gamma, there's a saddle point of the joint integral corresponding to gamma equals gamma naught, where gamma naught is the round metric on St minus 1. So that is to say that there is a particular geometry which is picked out in this path integral, which is a saddle, which is called the Hartle-Hawking geometry. And I'll show you what it is. So the basic idea then is that what we're going to do is to expand this slightly complicated looking integral around the saddle, namely gamma equals gamma naught, which corresponds to a bulk geometry which is the Hartle-Hawking geometry. And we're going to compute one loop fluctuations around that geometry in order to get the one loop norm. So I'll say that again in different ways. But let me first tell you what is the bulk metric corresponding to the saddle. So if the metric at asymptotia gamma is equal to the round metric on the d-1 sphere, then you can ask what is the bulk metric that it continues to at finite times. And the answer is that it looks exactly like this picture. This is the picture. And let me tell you, so it's the so-called Hartle-Hawking geometry, and here's one way to think about it. You can write down the metric for global de Sitter space in d dimensions. So here's the time part, and we see this is the usual cosh squared of t factor, which for t positive is exponentially expanding, times the round metric on the d-1 sphere. Now, the way to think about the Hartle-Hawking geometry is that it looks like global de Sitter down to time t equals 0, and then you smoothly glue on a Euclidean cap, a hemisphere. One way of implementing this is the so-called Hartle-Hawking contour. This is a slightly funky thing if you haven't seen it before, but it's very, very slick. What you do is that you take t, and you have t, the time coordinate, run along a complex contour. So this is the complex t-plane, this is the real part of t, and this is the imaginary part of t. So what you do is that as t goes, so we're going to follow backwards. So this is t going from positive infinity down to 0, and this red segment corresponds to the Lorentzian exponentially expanding part of the geometry. And then here, it takes a detour into the complex plane where it goes up to I pi over 2. And if you do this continuation, if you follow t along this contour, when it goes from 0 to I pi over 2, this actually becomes the Euclidean metric on the hemisphere, which is very nice. So that then corresponds to this piece. Okay, so if we go backwards, if we go from I pi over 2 down to 0, that prepares the Euclidean cap. And then when we go from 0 off to positive real t, that gives us the Lorentzian de Sitter throat, where it exponentially expands. And again, asymptotically, the metric up here is the metric on the round sphere. So as I mentioned, we're going to take gamma and expand it around gamma naught, the metric on the round sphere, plus small fluctuations through g times h. So these are small metric fluctuations around the metric on the round sphere at asymptotia. And it is in this sense that we are going to, this is the sense in which we're going to compute this inner product in one loop. This is the kind of expansion which we're going to perform. Yes?
Are you sure it's unique, the saddle point here?
It's believed to be unique.
Okay.
There might be some argument as to why it's unique, but It's at least believed to be.
Okay.
There's another ones nearby it. The question is whether it's the one with the least action is the question. Alright. So let's do this expansion around gamma naught plus root g times h, where h is the fluctuations. So this is the Hartle-Hawking wave function evaluated a little bit away from the metric on the round sphere. And this is in a slightly different notation, or other notation. So the answer that you get for this is you get some one loop prefactor times e to the s naught over 2, s naught is the de Sitter entropy, minus some Gaussian looking piece in H, expanded in hyperspherical harmonics. And then you get some of the higher loop correction. So let's understand the important features of the one loop wave function. I haven't written down the individual coefficients, but I can tell you what they are, but let me tell you what the structure is that's important for our problem. So let's just look at this Gaussian piece here. The part which is the Gaussian and the fluctuations, h, around the metric on the round sphere. So the structure is the exponential of some coefficient which has positive real part times the fluctuations hij and hkl contracted against a kernel. And I've written the kernel in a suggestive way. What the kernel is, this object here, is that it looks like the stress tensor 2-point function of a CFT on the d-1 sphere, which is a universal form. So that, I'm just writing this as a shorthand because it literally is the form of the stress tensor 2-point function of a CFT on the d-1 sphere. And that is the kernel that shows up in this exponential. You can argue this by virtue of the word identities, if you like. Now, one of the key features of this, so let me make two comments. Let's focus for the moment on d even, so such as 4 space-time dimensions, particularly close to our hearts, to avoid the complications of anomalies, although we can discuss what happens when there are, for example, Weyl anomalies. So the simplest way to understand this result, or a conceptual way to understand it, is that the late-time de Sitter wave functions behave like CFT partition functions in d-1 dimensions, coupled to sources including a metric gamma. This is a mnemonic. What I've said doesn't assume anything about DSCFT. This is just a calculation of the gravity path integral. But for those of you who are fans of DSCFT or the perspective that it encourages, this looks very much like a DSCFT type result. But it's really not. This is just organizing things by virtue of their symmetry. The key feature of this exponential is the following. This kernel is positive definite as a kernel on these fluctuations hij, hkl, which is to say that this Gaussian doesn't have any bosonic zero modes, and in fact it has no wrong sign modes. It's a perfectly nice Gaussian. Now, a comment about this is that we're used to thinking about gravity as having Euclidean gravity anyway, is having a conformal mode problem. There being modes that we need to, a conformal mode that we need to weak rotate, a wrong sign mode. That's not happening here. There's a different calculation. In the calculation of the late time wave functional, we're finding that the fluctuations actually form a perfectly sensible, positive, definite Gaussian. So we can compute, when we ultimately integrate over the fluctuations, we'll get a positive spectrum of fluctuations, which we can use, from which we can compute zeta function determinants as we like, but there's no modes that we need to rotate, and there's no zero modes that we need to handle in this wave function. That's a key feature. The other feature, an unsurprising feature, is that the wave function is SOD1 invariant. That makes sense, because this looks a lot like spin 2 fields on an SOD1 invariant background, namely the Hartle-Hawking geometry. So it's unsurprising that the wave function would inherit the symmetry. That's what you would expect. But just to point out, the combination of these two facts is very important. So it's important that it's both SOD1 invariant, and also that it has no bosonic zero modes. In other words, sometimes when there's a symmetry of an action, that the symmetry, if it can be associated with zero modes. It doesn't have to be, but in this case it's not. This is SOD1 symmetric, but it doesn't have any zero modes. That's fine, but I just want to note that because that's going to be important in a moment. So let me give you a sketch of the computation. I'll say what the individual steps are, and then I'll explain them in some level of detail, again, in a slightly different way. So here's the steps, but we'll say this a few different times in a few different ways. So the Hartle-Hawking state of one loop is a Gaussian over fluctuations of the metric at future infinity around the round sphere. That's what we've been discussing in the last few minutes. Now, the round sphere, gamma equals gamma naught, is a stable saddle point of the one loop norm. That's the thing that we need. To integrate over fluctuations, to integrate over these gammas, and in particular these h's, which are fluctuations around the metric on the round sphere, we need to gauge fix the diff times Weyl symmetry via Fedorov-Pavlov, or BRST, by, for example, fixing the non-transverse traceless fluctuations of gamma to vanish. That is, we can impose a transverse traceless condition on the gamma fluctuation. So to write this out, I'll say this more later, but just to have it on the board, as long as we have some board real estate here, we can take the Hij, and we can impose, for instance, that if I use gamma naught, we can impose some transversality condition as well as some traceless condition. So this is a transverse traceless gauge fixing in order to fix the diff times Weyl. So the key fact is that even though there's no bosonic zero modes coming from the wave function, there are ghost zero modes for residual diff times Weyl transformations that have not been fixed by the transverse traceless gauge condition, which correspond to SOD1 conformal isometries, which are symmetries of the wave function. I'll say this again in a moment. Therefore, we integrate over bosonic zero modes, non-ghost zero modes, and divide by the volume of the residual SOD1 symmetry, which is gotten by fixing the residual ghosts that are not fixed by this transverse traceless gauge fixing. So let me say that in a slightly different way. So you do this transverse traceless gauge fixing, and there are, if you look at the variation of the gauge fixing condition, you'll find that there are ghost zero modes corresponding to modes that have not been fixed by the transverse traceless gauge fixing condition. That corresponds to the conformal killing vectors on the sphere, which furnish a representation of SOD1. So that means that there's an additional SOD1 that has not been fixed by this gauge fixing. However, the wave function that we have is invariant under SOD1. And it has no bosonic zero modes to cancel out the ghost fermion zero modes. So upon fixing the additional SOD1, the additional SOD1 gauge redundancy, you end up getting an overall 1 over volume of SOD1. There's a very similar procedure to this that happens in the computation of the sphere partition function, but this is the Lorentzian Hartle-Hawking analog. So the answer that you get, ultimately, in one loop, well, you get some one loop stuff that has to do with the entropy. These are one loop fluctuations, and some one loop prefactor coming from zeta function determinants. But importantly, you get a division by the volume of SOD comma 1 that comes from these features that I described to you. And this was the result of this paper with Jensen from last year. Let me make a few comments about this, since this is a surprising result. It tells us that the norm of the Hartle-Hawking state, in pure Einstein gravity anyway, so far, is 0 to 1 loop. Now, I want you to compare this to the form of the sphere partition function. And you'll see that the answers look very, very similar to one another, but they have a few key differences. The first is that in the sphere partition function of one loop, there's these factors of I that I advertised at the beginning of the talk. Another difference is that there's a division by the volume of SOD plus 1, which are the killing vectors on the D-sphere, which is different than the volume of SOD comma 1, which are the conformal killing vectors appropriate for our Lorentzian Hartle-Hawking computation. And in fact, the fact that the reality conditions of the metric gamma force you into volume of SOD1, you can't You can't just willy-nilly wick rotate this or something into SOD plus 1. That would violate the boundary conditions that we've set up for the wave function calculation. Now, there's one other difference. You might ask whether these one-loop factors are the same. You know, there's these zeta function determinants, and we're not totally sure. We're trying to understand this, but my best guess at the moment is that in fact they are the same. There's some simpler examples in which they are the same. So this is related, Murdo, to your question before, is that, well, is there any, well, okay, you didn't exactly ask this. I don't want to put it, but related, maybe my answer to your question from before was that, is there any calculation at finite time that would give you this answer instead of this answer? And the answer, and it seems that there is, although we're still trying to understand this. There's a kind of Euclidean gluing, which is different from a Lorentzian interproduct, that would give you the sphere answer as opposed to the normal Hartle-Hawking answer. I can say more about this later on. Yes?
There's a basic confusion about this. So you're saying that given this complex time diagram you drew,
Yes.
if I think about this whole amplitude as being, this whole inner product as being, you know, the Euclidean time evolution, Lorentzian time, and then back again in Lorentzian time,
Yeah.
right, and then down. Why does it matter how long I evolve for in Lorentzian time and come back?
Good. So let me draw. So good. So let me explain this intuition. So let me rephrase your question the following way. So we have the Euclidean cap down here, and we have the Lorentzian throat, and we have the metric up here, and we want to glue this to this and this. So your comment, which is it was a very good one, is that, well, there's this Lorentzian part here, and this anti-Lorentzian part here, which should cancel, ostensibly, and then give us the Euclidean cap. There's two things about this which are, so there's two things we have to be careful of, which is why that intuition is not completely correct, which is that right now we're talking just about the saddle, not about the fluctuations around the saddle. So if you look at fluctuations of gamma, if you deform gamma away from the metric on the round sphere, and you ask what is the geometry that you would fill in backwards, it's generally going to be a complex geometry which does not cleanly separate between the Lorentzian and Euclidean part. So at the very least, that indicates that one has to be careful. So at tree level, you will get the cancellation, and that's why the sphere and the norm of the Hartle-Hawking agree at tree level for the intuition that you said. But at loop level, it's not clear for the reason that I said. Yeah.
So if this volume of d, SOD, 1 is coming from the killing vectors on one geometry,
Yeah.
one Lorentzian geometry, why don't we have volume squared?
Oh,
Because
because it's about the gluing.
Because
It's related to the gluing. There's only one division of diff times while.
okay, and it's coming just from the gamma path integral, not
Yeah, from the
not
resolution
from
of the identity of the gamma
okay.
path integral.
I see.
Any other questions for now?
Sorry, a very naive question, just to get some intuition. What is the scale? Is there an intuitive way to see the scale that makes the? I guess we are doing a semi-classical approximation, right? With saddles, etc. S0 very large. So earlier I remember you had some square root of g, but what is the dimensionless ratio? Is large here?
Well, how do I put this? So, so there's factors of g which are, so S naught is the de Sitter entropy, so there's factors of g which are baked into here, but how do I say, this is an effect which, how do I put this? So this is a fact, so these are factors of S naught to the minus d to the d plus 1, so there's factors of like root g up here, so as g goes to 0, this thing will vanish.
Yeah, but root g is not dimensionless, that's my confusion. Right?
Oh, sure.
What is the other scale?
I've thrown out. I've set many things to 1, including h bar, including the de Sitter length, and we can sort this out. But doing it in real time or imaginary time. Imaginary time might be better. By which I mean, yeah,
Maybe the cosmological constant or something else.
Yes,
Okay.
indeed.
So the subleading the dots will have also this volume factor downstairs, like the two loops.
Good. Yeah. So I'll comment on that shortly. So the short answer is yes. But that's.
So in perturbation theory would be zero at all.
It's 0 to all orders in perturbation theory. Although I'll explain why it's non-trivial to check that. But that's what. So the most recent paper from January checks this. So one comment is that in 3D gravity, the calculation is one loop exact. So 3D gravity is special. So it's kind of a topological theory, if you like. But it's one loop exact. And one comment, just an analogy, it's not a perfect analogy, but it's a good analogy, is that you might recall that the bosonic string partition function goes like 1 over the volume of PSL2C, which is also 0, or 1 divided by infinity. This is actually very similar in some structural way to the computation of the normal Hartle-Hawking and pure 3D gravity. They look sort of similar for a certain reason. But I just want to remind you that the idea that you can get quantities that are like the division by infinity, like these things show up in other contexts, such as bosonic string partition function, just as a point of connection. And this analogy, in the case of 3D gravity, is not an accident. And I would point you to some work of Collier, Eberhard, and Mollman from 2025, as well as work by myself, Christian Jensen, Alex Maloney from 2019 to explain some points of relation. Whoops. So, but related to the question that you were asking, so in 3D gravity, these corrections are 0, so that there's no higher loop correction, one loop exact. But in 4D, these corrections in general are you have to compute them. They're not, they're not. It's not a one loop exact. I mean, it ends up being one loop exact, but it's not obviously so. So let me just say for a moment why this is challenging, and I'll say more about this in the next slide. Like, what's the difficulty in showing this? So the difficulty is that, well, I erased them, but we're working in a transverse traceless gauge for these for the fluctuations around the metric on the round sphere. But when we say that the conformal killing vectors are fermion zero modes of the BRST apparatus, namely that if we look at the variation of the gauge fixing constraints, that there's 0 modes of that. That's a one loop statement. The difficulty is that the gauge fixing conditions become deformed at higher loops. You have to be careful about what you mean by the gauge fixing conditions of higher loops, and they receive corrections essentially from the fact that the geometry that you're fluctuating around has these root G contributions. So what happens is that the conformal killing vectors themselves and their compensating Weyl transformations are not 0 modes of the gauge fixing apparatus at higher loops, but there's a deformed version of them that still furnish a representation of SOD1. I'll say more on this later, but I'm just saying that the difficulty is that it's not that you get the conformal killing vectors in the higher loop calculation. You get some weird deformed thing, but it still furnishes a funky representation of SOD1, so it still works. I'll have more to say about this in a little bit.
Thanks.
Sure. So let's,
Can I ask?
yes.
So could I imagine that there is some unknown normalization factor of the wave function that drops from the computational correlation function?
Great. So one question, so a different way of asking this is the following. In the definition of the path integral, we have the ability to rescale it once by an overall constant. Of course, if we do a sum over topologies, we have to use that same constant everywhere if we're going to be consistent. But one comment about this is that, so you might say, maybe this is the thrust of your question, can we absorb this volume factor into a once and for all overall multiplicative constant in front of the path integral? Can we just multiply the path integral by volume of SOD1? So this is not a good idea for two reasons. The first reason is that if you look at the higher topologies, like if, let's say we're in 4 dimensions, instead of doing things on a 3-sphere cross-section, you could do S2 cross S1, for example. That S2 cross S1 breaks the boosts, so it's going to have a division by a compact Lie group. And it will have a finite inner product. But if you multiply the whole path integral by volume of SOD1, then it's going to diverge. So if you multiply by the volume of SOD1, you're going to cause all of the higher topological contributions, which would otherwise give convergent results to diverge because you're multiplying them by infinity. But the real thing, which I think was related to your comment about correlation functions, is the following. The thing that we're really supposed to do when we compute correlation functions is we have we're supposed to divide, we're supposed to compute something like this. If we normalized the path integral by an overall constant, it would cancel out in the numerator and denominator. So it wouldn't actually help us in the fact that this object now appears ill-defined because the denominator is 0. In other words, rescaling this by a constant and a constant will just cancel out, is all I'm saying. Was that really, does that answer the question you're asking me?
Yeah, I think the first answer was more convincing because I could imagine the volume is also both in the numerator. Division by volume is both in the numerator and denominator and cancels.
Well,
so it seems that you have actually found a way to kill this weird topology.
yes. Well, I think so.
Okay.
Maybe. Yeah, we'll talk about that later. But I still want to point out this. So one comment about this, which I'll say later. If you do enough insertions, okay, there's a second subtlety that we don't fully understand. We don't fully understand gauge invariant operator. What are the right gauge invariant operators to put in here? But okay, let's defer that. If you put in the right number of operators, you'll eventually break all the symmetries, and you can have the numerator have a finite answer if you put in enough operators, ostensibly. So you can get a finite numerator, because you still have to deal with this resolution of the identity that we described, but you can use some of the other operators to essentially to fix the SOD one, to fix the boost. But what I'm saying is just that if you multiply the numerator and denominator are both computed by path integrals, and my only comment is that if you want to have a good quantum mechanical interpretation where you have the notion of a Born role, then having an overall constant C in the definition of the path integral is not going to help you make sense of this quotient of objects. That's all I meant to say.
Then how we make sense of the 0 and the
What's that?
how we make sense of the 0 and the
Well, I think it's related to the comment that you would regard psi as a null state, and you have, so the no boundary state is a sum over topologies, and the conventional thinking is that the leading contribution to this, the Hartle-Hawking wave function, is the leading contribution, and that should give most of the answer, because it has the least action. But in fact, if it's null, then plausibly what you should do is start with the next topology. That's one thing you could say. I don't necessarily want to commit to that interpretation for reasons I'll explain later, but that's a line of possibility. Well, the reason I say that is the following, is that this actually contains other, there's other terms here is what I'm trying to say. There's other corrections to this that come from the higher topologies, both in the numerator and the denominator. So the denominator is not actually 0, it's just the Hartle-Hawking part of it is 0.
So is it in some sense like saying that with the analogy of the bosonic string, if you do the partition function not on the sphere but on a higher genus surface, then you don't find the volume?
Yeah, for instance, it's related. Yeah, I mean it's a different computation, but that's the right idea. That's what okay. So let's talk briefly about features of higher loops. So first, let me be a little bit more explicit about the one loop ghost that I was drawing on the board. So again, let's let gamma equal, let's look at small fluctuations around the metric on the round sphere. And as I mentioned on the board, to fix gamma ij modulo diff times while, we can impose the gauge fix, the transverse and traceless gauge fixing conditions. This is the transverse one, and this is the traceless one. So, if we look at the variations of these gauge fixing conditions under diff and while, so our diffs are here psi and our while rescalings are sigma, then at one loop you get these kinds of equations plus corrections of higher loops. And these equations, if you like, these are related to the kernel of the ghost action, or the quadratic form. And if you want to figure out in one loop, you can simultaneously set the variations to 0 if you choose psi to be a conformal killing vector on the d-1 sphere, and sigma to be the compensating while rescaling. Basically because the second equation essentially forces sigma to be related to psi by, in a simple way, and when you plug it into the first equation, it becomes the equation essentially for the conformal killing vectors. That's what happens. Now, the difficulty is that even though these equations, when you throw out the order root G pieces as you're supposed to do at one loop, so at one loop you just consider these, the order 1 parts, not the order root G parts, that setting these both equal to 0 give you solutions corresponding to conformal killing vectors, but as I was mentioning before, if you want to do this to higher loops, you have to start including these order root G and higher order corrections. So therefore, the equations that you're solving are not going to give you diffs that correspond to the conformal killing vectors, but diffs that are much more complicated, that have these sort of infinite series and corrections of root G. So you have to figure out how to deal with that. Now, what's interesting is that you can find simultaneous solutions to the variations of the gauge fixing conditions to all orders of perturbation theory in root G. And therefore, if you wanted to know whether this was true in all loops, the answer is yes. And there's an argument in this recent paper that constructs these deformations of these diffs which at leading order correspond to conformal killing vectors while rescalings. So there's this sort of this deformation of these objects, but interestingly the diffs still form a representation of SOD1. So there still is a volume of SOD1 in all the terms of perturbation theory. You also have to show that the wave function is invariant under those deformed transformations, which you can also do. Now, let's suppose we add Bunch-Davies matter. So far we've been talking about pure gravity. If we add Bunch-Davies matter, then that does not change the form of the result. So let's just talk about what happens at one loop, but it's sort of similar at higher loops. So suppose that we have a scalar phi, which at asymptotia, its asymptotic data is described by chi. So chi is like the description of the field, for example, at asymptotia. It's the analog of h for the metric. So in one loop, so if you jointly prepare the matter field in gravity and in the no boundary geometry, specifically the Hartle-Hawking state, with the SD-1 sphere cross section, then in one loop, the wave function factorizes into two pieces. One is the one that we described before corresponding to gravity, and then there's another one that is essentially the one loop Bunch-Davies wave function for a scalar field. Now, at higher loops, these things can become entangled with one another. I mean, meaning it doesn't factorize, but okay. I'll tell you what happens with that in a moment. But anyway, at least at one loop, a comment is that each of these terms in the product is individually SOD1 invariant. So essentially what happens, more or less, is that the full Hartle-Hawking state, by here I mean the one with matter and gravity together, factorizes into two pieces, one of the norm of the Hartle-Hawking state in the absence of matter, and then here is just the ordinary field theoretic norm of the Bunch-Davies state, which is finite in zeta reg. So this term is 0 because it gives you this 1 over volume of SOD1, and therefore the product of these is also 0. And well, it's more complicated what happens at higher loops, because when you look at higher loops, you're also essentially looking at a Bunch-Davies wave function on a slightly deformed background, but you can show that that by a slightly more complicated argument that this 1 over volume of SOD1, 1 persists at all higher loops even when you couple the Bunch-Davies matter. So the matter, coupling to matter doesn't affect the result that I described. Now, I'm assuming that the Bunch-Davies matter is sort of ordinary matter. I'm assuming that this doesn't have any bosonic zero modes, which for ordinary matter it will not have. So I'm saying you can cook up some weirder examples in which that you consider matter in which you will, a Bunch-Davies scalar that has some weird symmetry that you gauge, and you can sort of by hand construct something that has a weird bosonic mode. But let's assume that that's not the case. That won't happen for ordinary matter that we care about.
Do you expect in general this factorization?
This is true in general of one loop. Basically because the Bunch-Davies vacuum, the Bunch-Davies phase is defined around the Hartle-Hawking background. So around essentially the spacetime corresponding to h equals 0. So a very natural and important question, which is rather subtle, is what happens for the slow roll inflation. Okay, well, so an important example of a field that you might want to couple this to is the inflaton. If you want to study, for example, cosmological perturbation theory. So I won't say too much about this, but if you're in the slow roll regime, so this is some particular parameterization of the slow roll regime, in which the space-time looks basically like de Sitter. So you find a similar result, of course, that it factorizes at one loop between the Hartle-Hawking, between the gravity contribution and the inflaton contribution. And let me make a few comments. The inflaton wave function has a term that is like e to the minus a constant times the derivative of the slow roll potential times the zero mode of the asymptotic value of the inflaton. And there's also Gaussian terms. So there's two things to say. The first is that the one loop inflaton wave function is SOD1 invariant. So there is still going to be this division by volume of SOD1 even with the inflaton. So the inflaton is not immune from this argument. However, the inflaton has a different feature which is a little bit puzzling that has been noted in recent work that I want to flag for you. Because of the fact that the inflaton doesn't just have Gaussian pieces, but because it has this piece, which is this exponential term, that has a linear dependence on the field. Well, what this means, if you try to minimize the probability, if you like, if you try to find the probability minimizing configuration of the inflaton, it would force the inflaton to undergo, in the conventions that I've chosen, as little inflation as possible. It forces it to be sort of as like very low down in its potential. So this is a pathological feature of the Hartle-Hawking state that has been noted well, it's been noted for many years, but there's a nice recent review of it by Maldacena, which articulates this in a nice modern way. But the point is that the Hartle-Hawking wave functional is pathological because it actually predicts that we shouldn't have that much slow roll, and therefore that the spatial curvature of space-time should be very, very large, which it's not empirically. So I want to point out that this feature is here, but the problem is that if you take this at face value, if you assume that you're in the slow roll potential forever, then the one loop inflaton wave functional is not normalizable because it has this exponential term in the zero mode. And this an integral, if you integrate it over all phi naught, then you would get a divergence. So really what's going on, of course, is that in this calculation, what you should really do is you should understand that if you make the fluctuations of phi sufficiently large, then you're not in the slow roll regime anymore, or that you're gluing onto a hat or a flat space or whatever. So that will have to enter in, but at least at some formal level, in the formal one loop computation that you would do in sort of a small G Newton, or in this type of expansion, it is the case that the slow roll wave functional is SOD1 invariant. Okay.
Isn't it a bit counterintuitive? I would have expected that since inflaton gives a preferred time slicing, it should break SOD, 1. In fact, sometimes there are arguments that these isometries are non-linearly realized by the fluctuations of the inflaton, which sounds as if you are actually reintroducing the zero mode.
Yeah,
also only zero.
So that's a good question. So let me disentangle two aspects. So the first is that what we're doing, so if you fix the value of the inflaton, then if you fix a background of the inflaton, if you like, then that's like fixing a clock. That's part of the intuition that you're saying. So the thing that we're doing, at least at asymptotia, right, is that we are expanding around, at least for all of the non-zero modes, around phi equals 0. And we're sort of integrating over all values of the inflaton when we do the gluing. And that essentially around phi equals 0 ends up giving you restoring SOD1 invariance, because it's not like fixing the value of the inflaton, it's sort of expanding around phi equals 0, which is the saddle, at least for the Gaussian parts of the calculation, and then integrating in fluctuations around that. But a confusing aspect of it, which I still don't totally understand yet, is the following. At asymptotia, the wave function is certainly SOD1 invariant, but the natural gauge fixing at finite time, which is closer to the gauge that one does when one ordinarily does inflation, does indeed look like the inflaton acts like a clock. So it's confused. So how it is organized at finite time is sort of puzzling for the reason that you said. However, there is also an analogy with this, with when you try to compute the Hartle-Hawking wave function norm at finite time, even in pure gravity. Because in pure gravity, it's natural to use at finite time York boundary conditions in which you fix a constant mean curvature condition. And the curvature, it doesn't really act like a clock, but it does change as you move through time slices. It's sort of like it's like a kind of like a time variable. So anyway, in the finite time calculation, the answer, we believe, is ultimately independent of this sort of fiducial clock that's induced by the particular way the gauge fixing and slicing is done. And the answer is ultimately independent of it. And what I wonder, although I don't know yet, is whether this is also true in the inflaton case. So the short answer to your question is, I agree with your intuition, and this is most manifest if you do the calculation of the inflaton at finite time, which is something that we're trying to understand. But at infinite time, at asymptotia, which is not the ordinary way that we do things, it's the wave function is SOD1 invariant. So I don't know quite how to square those two facts, but my best guess is that at finite time, there's a reorganization of the calculation in which one has to be very attentive to the issues of the finite time gauge fixing to see how this works. So one
So
of the,
just to understand the bottom line, you speculated maybe this infinity cancels the zero in the last point, or
well,
this problem goes away.
I'm not sure that's what I would say. I mean, well, first of all, they're different. One naive thing to say is that they're actually, like, if you sort of look at the strength of the divergence, actually I think this is actually a stronger one. But they're also kind of unrelated to each other. So I think that the status of this is not clear. But the real answer is that you're sort of, I guess, one is that, the first is that once you do the slow roll computation at finite time, which is something that we're trying to understand for the reasons that Merdad was asking about, just to make sure that one understands what's going on. Because it really does look different at finite time for the inflaton than at infinite time in some confusing way. And the second thing is that that we're also thinking about is that you should go slightly outside the regime of slow roll, which would actually break the SOD1. So, but how it does so quantitatively is an interesting question that we're trying to understand. Okay, so something else that one might do, which is in fashion these days, is that you might want to couple to a world line, an observer if you like, a world line with a clock. So you can ask what happens in this case. So suppose that we couple to a world line. So this is a nice model of a world line with a clock due to Witten in this paper from 2023. So you take this Q to be greater than or equal to 0, you take P, which is the conjugate momentum, to be along the reals, and as such the Hamiltonian with the observer is mass plus Q, and since Q is positive, it tells us that the energy of the observer is greater than or equal to the mass m. So this is a model of the world line with a clock with a kind of continuous set of states above this energy m. So P, if you like, is the time variable, and its non-compactness leads to a continuous uniform spectrum for Q. All right, so what happens when you couple this to Hartle-Hawking? Well, essentially you get a world line that, like the saddle anyway, looks like a world line that goes to infinity, but then it also, in the saddle, it sort of dips down through the Euclidean cap, and it comes off at a antipodal point and goes up to asymptotic infinity. So for those who are familiar with world line calculations, you might be used to understanding that there should be a world line in the static patch and a kind of anti-world line in the anti-static patch. This is some analogy for this. So if you glue together the bra to the cat, you end up getting an answer which is finite. And let me briefly tell you why. So when you couple a world line with the clock, you are breaking SOD1 to SOD minus 1 cross SO11. So there's still an SO11 factor remaining, which is still non-compact, which is related to boosts along the observer, along the observer's world line. However, in this model, because of the fact that there's a continuous spectrum for Q, if you like, there's a kind of a global time shift, bosonic zero mode, that you have to account for. And roughly speaking, the bosonic zero mode of the time shift soaks up this factor of SO11, so you get a finite answer. So therefore, an observer with a lot of entropy, because of this continuous uniform spectrum, gives a finite inner product. it soaks up the non-compact part of the divergent. So this suggests a connection to this recent work in the context of understanding de Sitter using von Neumann algebras. But I'd like to point out that I'm not sure whether this calculation is a red herring or not. I just want to observe why. So when we do cosmological perturbation theory, we don't ordinarily couple to a world line or an observer with a lot of entropy. We really do the thing where we couple to Bunch-Davies matter or an inflaton. You know. So it would be very confusing, at least to me, if the thing that one had to do to get finite answers was to kind of post-select on the existence of some observer with a lot of entropy in this case. Like it's not what we do in cosmological perturbation theory anyway, so that would be puzzling. And of course, it also doesn't work if you have an observer with a discrete density of states. I mean, you really need this uniform. You really need this continuous spectrum in order to get this to cancel out this SO11. So anyway, this is a calculation which is suggestive, but I'm not sure I can offer a good interpretation of what it means. So let me conclude. So we've studied the quantum mechanics of the Hartle-Hawking state, the Hilbert space in which it lives, and its norm. The norm is 0 to 1 loop, even with field-theoretic matter, and moreover, this persists at higher loops for normalizable Bunch-Davies states. An important exception to normalizable Bunch-Davies states is the inflaton, which still has some confusions we're trying to understand. That's obviously a very important case, so it should not be ignored. So, related to some questions that were asked before, this further brings into question the phenomenological relevance of the Hartle-Hawking state, namely the contribution with sphere cross-section, and what may replace it. But I would caution you that before one announces, the death of the Hartle-Hawking state, one needs to really understand carefully what happens with the inflaton, because that's actually the case we care about. Now, one reason, by the way, why one might want the Hartle-Hawking state to go away, regardless of, okay, so here's a motivation for motivated reasoning, is that this feature of the Hartle-Hawking state that I mentioned, that it forces you to have a small number of e-folds of inflation, which very much disagrees with the experiment, is bad. So you might want to say, let's get rid of it. I don't want that. I want these other contributions to the no boundary state which don't have that problem. Okay, well, whether the mechanism I said gets rid of it when there's an inflaton is not so clear, but one may wonder. Let me conclude with a final speculation that I mentioned before. So in this talk I've argued, let's just talk about in pure gravity, that the norm of the Hartle-Hawking state is 0 to 1 loop and in fact to all loops in perturbation theory. Now, what about the norm of the how do we get the sphere answer? What kind of gluing gives the sphere? So these equations that I'm about to show you are not real equations. They're just sort of impressionistic cartoons. But I just want to give you some suggestive thought. Suppose there's a pairing, which might not even be the same pairing as here. Even though these all look like bras and kets that are glued together with the same inner product, let's not limit ourselves to that possibility. But suppose in this case I wanted to glue, the ket to the ket, where k is like a complex conjugation operation. So it'd be like gluing a ket to a ket instead of a bra to a ket. Well, you might wonder, maybe, can I get these factors of I? I mean, it doesn't have to be real anymore if you glue a ket to a ket, and how do you do the gluing? Or if you glue the bra to the bra, do you get minus I times d plus 2 times, okay. So is there some way that there's alternative gluings that are not the ordinary one that we would want to do for a Lorentzian inner product, which in fact would give us the sphere partition function computation of Polchinski, and then its complex conjugate, the anti-sphere partition function, if you like. So this is something that we're currently trying to understand, but it would be very interesting if there were, to pin down the sense in which there are multiple possibilities for inner products or gluings, which would then relate these different results to one another, both the sphere and the norm of the Hartle-Hawking. That might also bring into connection the fact that the Hartle-Hawking state, so the sphere partition function encodes information about the de Sitter static patch entropy, and the Hartle-Hawking state in a more indirect way does it as well, and is sort of connected to the sphere, but not exactly. So the connection between all of these objects, the sphere, the de Sitter entropy, and the norm of the Hartle-Hawking might be better connected by elucidating what these cartoonish equations down here might be. So with that speculation, let me thank you so much for your time.
So I'm a bit confused by this comment about the observers. It's essentially eliminating the zero. Because in the computation, when we couple to matter, we said that at one loop, everything just factorizes. I guess one loop meaning one loop for both,
Yes.
right? And then we also get a zero. However, you can think about the observer as a very much off-shell configuration of the matter as well,
Yeah.
right? Like a very concentrated lump of matter that you approximate
Yes.
as an observer. And that would tell you that you maybe in the saddle point approximation for the matter, indeed everything vanishes, but there are some off-shell configuration or far away configurations of the matter which are actually more dominant than this saddle point, which again vanishes because they actually do break, I don't know, the S or D, 1 symmetry. So is there a concrete way of just seeing if there are such configurations?
Well, I would say that there's 2 points of view. One is that I would say that the world line of the clock is non-perturbably related to the matter computations that have been described. The other thing, of course, which is complicated, is you have to build the clock, or you have to build the continuous degrees of freedom internal to the observer. So they're at the very least non-perturbably related, so there's no contradiction at a technical level. But a related comment is the following. Sometimes it is useful to think about the observer as a kind of tube, where you're sort of excising some kind of some disk, if you like, across time from the space-time. In that sense, it can be in certain cases a bit like you're looking at a different topology, because you sort of excise this tube from the space-time. That's another way of saying that if we generally think about different topologies as being non-perturbably related to a fixed topology. So that's another intuition, if you like, as to why it's non-perturbably related to the computation of Davies matter.
We have many questions already, and I think that means it's time for lunch. So thank you, Jordan, again.